Good afternoon. When you change the way you look at the things you look at change. India celebrating 75th Indian independence in the name of Azadi Ka Amruta Mahotsav. We also celebrating by dedicating our talks to it and creative. Creativity and activeness together creative. Creativity thinking leads to activeness and activeness needs creativity. So creative tagline is knowledge square. Sharing of knowledge increases our knowledge. Creative is a group of people who are very curious to know the new knowledge or something want to learn more. Vision of creative is to build constructive thinking progress in various fields. We focusing on non-textual, non-academic, non-syllabus related concepts. Creative creating a platform to the resource person to share their discoveries, view, evaluations with interesting peoples. Creative is always thankful to our resource persons for sharing their knowledge with us. And we are organizing weekend talks on every Saturday between 3 to 4 p.m. on Zoom platform, and also we live streaming our program in our YouTube channel. We have WhatsApp group and social medias where you can follow us for more updates. Today is 39th episode of Creative. Today's topic is quantum computation and information theory, new world view and its technological impact. To present this, we have Mr. Aravinda S today. I welcome our speaker and all associates and creative participants for this session. And I invite Professor Ishrat Sultana to introduce today's speaker. Over to Ishrat.
Thank you, Supriya. Am I audible?
Yes, yes.
Okay. Hello, good afternoon, everyone. Distinguished participants, today's speaker, Mr. Aravinda C., my dear friends and associates of Creative Knowledge Gauribindur, I am pleased to welcome you to our today's webinar on quantum computation and information theory, new world view and its technological impact. At first, I am glad to introduce you to our today's chief guest and speaker, Mr. Aravinda S, who is a theoretical physicist, assistant professor at the Department of Physics, Indian Institute of Technology, Tirupati. Apart from being physicist, he also writes poems, prose in his native language, that is Kannada. I am also glad to tell you that Mr. Aravinda C is my classmate and he is also an alumni from our National College, Gauribindur. So Mr. Aravinda C started like this. In search of the path to explore and understand the phenomena of the universe around him, he took up a bachelor's degree in basic sciences and completed his master's in physics from the National Institute of Technology, Karnataka, Surathkal. After the master's, he spent some of his time at Raman Research Institute as a visiting student, where he happened to meet Dr. R. Srikanth and ended up discussing with him various foundation topics in quantum theory. By the virtue of being the first rank holder at NIT in his master's, he was able to secure the prestigious Inspire Fellowship of the Department of Science and Technology, Government of India, to join Dr. Srikanth as a PhD student at the Purna Pragna Institute of Scientific Research, Bangalore. This PhD was in affiliation with Manipal Academy of Higher Education, then called Manipal University. So, at the end of December 2016, he finalized and submitted his PhD thesis and joined the Institute of Mathematical Sciences, Chennai, as a postdoctoral fellow. He defended his thesis in June 2017. 2 years later, he visited Professor Guru Prasad Kar at the Indian Institute at the Indian Statistical Institute, Kolkata, for about 6 months. During this time, he was looking to extend his field of study and to acquire new tools. He approached Professor Arun Lakshmi Narayanan of the Indian Institute of Technology, Madras, with a proposal involving using the information theoretical tools to understand the dynamics of the quantum many body systems, especially the quantum chaos. I welcome you, sir, on behalf of Preem Creative. I would also like to welcome Srinath, sir, who is the driving force behind our team. I welcome you, sir. I would also like to welcome all the associates and the participants of the creative group. I hope you all will understand the value of quantum physics and its need for the future. I ensure you all that this webinar will be profitable for you in every aspect. This is all from me. Thank you all for being such a patient listener. Thank you.
Thank you,
Over to you,
Ishrat.
Supriya.
Thank you very much. Arvind sir.
Yeah.
I want to welcome Satyendra sir, Venkatesh sir, Girish sir. So many National College alumni names are here. We are very happy for coming, sir. Over to Arvind sir.
Yeah, thank you. First of all, I am very happy to see Satyendra sir. I have tried to contact him in a long time. I could not. But thank you, sir. Thank you very, very much. I still remember all the help you made me during my days in during my PU and then during my degree and the scholarships which I have received. I still remember every year. I remember that all my college fees used to be borne by the scholarship which I used to get it from you people. So thank you very much. Thank you, sir. And yeah, so and thanks, Supriya. Thanks for all these things, and thanks, Ishrat, for a nice introduction. Only one small correction, Dr. Aravinda, not Mr. Aravinda. just a simple thing. Otherwise, Aravinda is also fine. Just Aravinda is also fine. Okay. So, and also I would like to thank Srinath sir. Srinathana, yakendre I remember my first motivation that I have to do my PhD is during my 10th standard, I suppose. I visited ISRO when he was doing his PhD at that time. So he took around me to all the instrumentations and everything. So I saw there, and then it was a different kind of motivation. So I would like to thank him that that was my starting kind of thought. That's a seed where it took place. Okay, so with all these things, let me share my screen and start.
It's visible.
Visible, right?
Yeah. Yes.
Okay. Okay. ನನಗೆ ಅಲ್ಲಿ ಮೆಸೇಜ್ ಆಗಲಿ ಬೇರೆ ಏನಾದ್ರು ಬಂದ್ರೆ ನೋಡಕ್ಕಾಗಲ್ಲ. If anything, just let me know.
We discussed that last.
Okay.
Just one point, Aravinda, just one point, just for the benefit of audience, I would like to inform that his book written in Kannada has been shortlisted in Kendra Sahitya Academy Prize. It was 6th in the list. Unfortunately, he could not get within the top one. This is the information to audience. He is a very good lover of Kannada. He is as Ishrat was telling, poet, and he is writing poem. It is a proud moment for all of us, physics and Kannada going together. Thank you, Aravinda.
ಥ್ಯಾಂಕ್ ಯು ಆಕ್ಚುಲಿ ನಾನು ಕನ್ನಡದಲ್ಲೇ ಮಾಡೋಣ ಅಂತಿದ್ದೆ, ಬಟ್ ಆಮೇಲೆ ಬೇರೆಯವರು ಇರ್ತಾರೆ, ಸೊ ಅದರಿಂದ ಇಂಗ್ಲಿಷ್ ಅಲ್ಲೇ ಮಾಡಿ ಅಂತ ಹೇಳಿದ್ರು ಸುಪ್ರಿಯಾ. ಸೊ ನಾನು ಮಿಕ್ಸ್ ಮಾಡ್ತೇನೆ ಎಲ್ಲಿ ಮಾಡ್ತೇನೆ. ಸೊ ಓಕೆ, ಸೊ ಲೆಟ್ಸ್ ಬಿಗಿನ್ the talk. So it's all about quantum computation and quantum information theory, the new world view and the technology, etc. I'm from the Department of Physics, IIT Tirupati, and this is my group. These are the fields which I work: the quantum foundation, information, and computation. I have basic interest in these four fields, which is been expressed here. One is sorry. So um, one is physics, philosophy, mathematics, and the engineering, which covers quantum foundation, information, and computation. So where am I? So you all can see that the nice structure. So you must have all heard about the Tirupati because of the Venkateshwara, and now there are two premier educational institutes, central institutes. One is IIT Tirupati, and nearby is ISER Tirupati. Both are situated between the 5 kilometers, and this is the transit campus actually. There is other main buildings are coming up somewhere. I think somewhere here, or other buildings are coming up. But as of now, this is the constructed area, and these are the hostels, and then there are some classrooms, libraries, and then labs, and then faculty quarters, and all those things. So that's what it's coming up, and around some 500 to 600 acres. So we are. This is the picture what you can see now. So it is situated away from Tirupati, towards uh, Kalahasti. So it is just in between Sri Kalahasti and Tirupati. So around 10 to 15 kilometers from before Kalahasti. So this is our campus. I invite all you people to visit the institute and see that. Okay, so let me begin the talk. So why quantum? What is so great about this? Let me tell you. I'll give you what is the amount of information capability that it is going to possess. So, what is the information? What is its information capability? So, recently, just using, I'll come to tell you what is the mean by qubits and all other things. But just using some 52 qubits, which is similar to 52 bits. 52 qubits of one of the quantum computer in the Russians, by Chinese. They were able to show one computational problem. There exists one computational problem which takes nearly 4 into 10 to the power of 4.6 into 10 to the power of 4 years in a very highly efficient classical supercomputer. So this is the amount of time it requires to solve that problem. Okay, whereas in the quantum computer, they showed it. This is an experimentation. This is not a theory. So in the existing quantum computer, they were able to show it that this problem can be solved in nearly 4.6 hours. You can see the difference, 10 to the power of 6, nearly 10 to the power of 6 orders of difference when it comes to the computational power. So this is the amount of computational power and speed that quantum computers is going to provide. Next, then the second thing, the information, secure information. So what is the current status? So current status, we have a success, there is a success intercontinental secure information. Here, the security, normally when we send information like what we are speaking, our classical phone or our classical cryptography, banks, and every details, all these things are secure under some mathematical assumptions. The standard assumption is the complexity of solving some mathematical function. That is what is hidden in all the secure communications. Whereas in the quantum communication, the security comes from the nature, in the sense that no intelligent being can crack the security. So that's an important aspect of the secure information, which You can see in between it is nearly there is a secure intercontinental secure information transfer is being experimentally conducted between China and Europe. And currently, lot of Indian agencies, including ISRO, DRDO, are all conducting. Even in Indian system, ISRO along with RRI started a space mission, using the satellite to quantum secure communication, and that's going to be the next industrial revolution. So in the industry, where is it going to be used? Molecular simulation. The one and most important place is molecular simulation. Almost everything in next. Why molecular simulation? So why can't the classical computers? See, in the classical computers, simulating, for example, in order to simulate, I am going to tell you the numbers, but roughly, simulation is very difficult in classical computers. However, supercomputers is. So, drug simulation or molecular simulation, in some sense, it is impossible. Whereas the quantum computers are going to provide the enormous skills to molecular simulation that will drive the drug industry. So that's a major out going to be. And the another one, the most important one, as already people started to use all this. What I'm saying is not the future technology. All these people are already using them, and many of my friends are in these industries where they are using the quantum computers to some of these aspects. The second most important thing is finance, stock market optimization, and everywhere. So they have started to use in the finance, and wherever the machine learning based protocols are running, one can use machine learning based algorithms along with the quantum computer to make it more efficient. So there is a huge demand on the quantum information and computation. And where are we? You can imagine that in 1980s, what is the status of classical computers were there. That is the time we are in with respect to quantum computers. And you can imagine with the 30 years, the development which is you are now seeing, and the 30 years of the development with respect to quantum computers is going to change the world entirely. So now already the big companies are investing, and then big companies are running. For example, IBM, they already have a 128 qubits computers. All of them are having, Google is having the computers, Honeywell is having the computers, Rigetti, all of them are already building the computers and the quantum computers. And all these requires the very low temperatures. So when we are doing the computations, this one has to do it in the cloud. That means we will be giving the jobs, and the computers will be somewhere else. This is the current status of quantum information theory and the quantum computation. Okay, so what is it? When it comes to quantum computers, what is it? When I'm saying all these things, and then what is it? First of all, it's not an upgradation of classical computers. What I mean to say is that whatever the amount, however supercomputer it is, the classical computers run in a very different framework, both from the hardware, software, and including the formalism. Everything will be different. Whereas the quantum computer is entirely different. What is so different is that in the classical computers, everything runs in between bits. That means either 0 or 1, and then you have a string 0, 1, 1, 0, 0, some things, and then transformation of these strings, and that's all what we are going to get. All our information exchanges between this one only. Whereas the quantum computers, I'm just indicating, I'm planning to use as minimal mathematics as possible. So when I'm saying something at some time, because of the constraint in the language of using the English, sometimes I may not be able to sufficiently explain its idea or miscommunicate also. because the only way to properly communicate is the mathematics, and that I don't want to use it today for a general public talk. So there are the possibility of miscommunication. If something is strange, please check with me. So, okay. In the quantum computer, there are two steps, just like 0 and 1. So this is called get 0 and get 1. What is the greatest possibility in quantum computer or in the quantum mechanics is that in the classical, either 0 is allowed or 1 is allowed. In quantum, both 0 and 1 is allowed. And any superposition of 0 and 1, whatever the weightage you are going to give it for 0 and 1. This, what I mean to say is that it's completely based on the classical logic. So either yes or no, whereas in the quantum, yes and no is possible. So that gives the enormous amount of power. That's such a simple change in the logical system will provide the enormous amount of information theoretic capability. For example, just think, so these are called the qubits. These are called the bits, information carriers. In the quantum, it is called qubits. So how many, in order to give you the picture, for example, if the computer is having 21 qubits, the amount of information that one can manipulate with is this much of dimensional system. So this is the dimension of the vector space, or this much of classical information can be in some vague sense can be handled by just 21 qubits. That's the power. So if the number of qubits increases, the amount of information capability increases exponentially. So something, if one is having 100 qubits or 1000 qubits, 2 to the power of 100 or 2 to the power of 1000, no classical computer, whatever the powerful it will be, can beat it. So that's the amount of power. This is about the quantum computers. Okay, so we all think that technology happens once we think about this technological development or all other things, but what is basic fundamental development is because of some deep questions or some deep philosophical questions. Always in the technology, not only many technological developments are due to an answer to some deep question. All these things started from what we nowadays call the quantum mechanics, and whatever the developments today is happening goes back to 1930s. And there is a famous debate between Einstein, Bohr, and Schrodinger, who are the founding fathers of quantum mechanics. I'll going to explain what are the quantum mechanics and all. And there were some questions addressing, can the quantum mechanical description be considered complete? And the debate between Bohr and Einstein, that was in some sense the origin of the technological development what we are seeing it today. Okay, so before going to quantum mechanics, what is our classical mechanics? Means what is our classical world which we see are all around us? Our classical world, the world which we see outside, is deterministic. What do you mean? What do I mean by deterministic? Whether everything can be known with certainty. So there is a bit trick here. I would say that I don't know what is going to be happen tomorrow in the weather, and many things we don't know. But that uncertainty is not because there is an inherent uncertainty. Instead, the uncertainty is because of we don't know. That's the situation in the classical mechanics. In the classical mechanics, if given enough information, if the information is sufficient, then everything can be known definitely. For example, to give a simple example, if I am tossing the coin and if the coin randomness whether head or tail, is it possible to know? If of course it is random, in the first view. It's not possible whether it's head or tail, but given enough information about every aspect, what is the force with which I'm tossing the coin and the weather, every information taken into account, then it's always possible to deterministically and exactly predict what is going to be happen next. Moreover, that the very assumption that whether I observe it or not, I don't know the outcome, but outcomes always exist. For example, if I'm tossing the coin, whether it is head or tail, I don't know when it is reflex, but definitely whether I know it or not, head and tail exist without my observation is the crux of the classical world. Whatever we see around us is basically because it exists whether I see it or not. There is a famous quote by Einstein when he was walking. He asked, "So is there a moon if nobody looks?" So I think in somewhere in Indian philosophy there is a related question also. If the tree falls within the forest, will there be a sound? I mean, if someone hears the sound or not. So without our observation, is there the world will be there or not? According to classical mechanics, if one observes or not, the world exists. So that's our classical world. So um, Einstein was a classical physicist in one sense. He was a realist in some sense. It's a debatable issue whether he's a realist or not. Let me quote his little bit normally quoted sentences. Any rate convinced that he does not throw dice. That means world is deterministic was his view, whereas Bohr was saying that Einstein stopped telling God what to do. So Bohr was kind of epistemist. So yeah, let's not get into that convention. One more thing. So again, when it comes to the quantum mechanics, for example, so we can see that this is a circle, and there are many properties. So this one is color. Color is a property, for example. So this is a red color, this is a blue color, and this is green color. And the shape is another property. For example, this is a square, this is triangle, and this is circle. There are the different properties, and the size. One is big and one other is small. Remember, these are the properties and these are the outcomes. So, but all these properties are simultaneously knowable. If I ask any, what is it? So if I ask what is its shape, I can clearly say that it is a square. It is a square. And what is its color? It's a red. And what is its size? It's big. All these three properties can be simultaneously accessible to a classical system. Whereas within the quantum mechanics, there exists a set of observables that cannot be jointly knowable or cannot be jointly observable. We all heard about famous Heisenberg's uncertainty relations, that position and momentum cannot be known explicitly. Like that, there are infinitely many set of observables which cannot be observed simultaneously. What does it mean? If I cannot observe two properties, does it mean that the property itself doesn't exist? What I mean to say is that, for example, let's imagine a person who has a color blinded between red and blue. Okay, red and blue. So if he cannot distinguish between these two, so that means he cannot differentiate between this square and this square. So does that mean that these two are different color or not? So this is the question. So since within the quantum mechanics, it is not possible, there exists set of observables which cannot be jointly knowable, then doesn't it mean that the property itself doesn't exist? This is the one question bothered Einstein, Bohr, and everyone during the 1930s, just after the completion of formalizing the quantum mechanics. Okay, so now that's the situation. Now comes to the what is quantum mechanics, if I am asking. So I have explained in some sense, but to In that sense, what is a theory? If I'm saying, if I wanted to know what is a theory, normally we do an experiment. So there is an experimentalist, and so let me go back here. So what is an experimentalist is doing? So in every experiment, there will be some preparation. Something is being prepared, some material is prepared, whatever it may be, and it is transferred. Some way it is transferred, and then it is measured. And once you measure, you have a data column. So all of us have some tabular column of what is the probability with which you are getting. So for example, in previous slide, when I'm explaining the colors, shape, and size, if these are the three properties, and if I'm preparing one of the color, and then you are measuring it, it is a red or blue, and then you're tabulating the column, and with some probability is. A theory is the mathematical representation of what we observe in the experiment, or what we observe in the universe, or observed world. So there is a world and an observer and a theory. So an observer always constructs a theory. There is a world and he observes it and constructs a theory. So theory is a mathematical representation of our observed world in such a way that it should be as minimal as possible, and it should be able to provide the predictions. So it should be able to predict, and it should be able to predict an experimental results. In the quantum mechanics, there is a mathematical framework. It's called the Hilbert space. Every system is represented as a vector in the Hilbert space. Measurement is represented as an operator, and there is a famous rule how to calculate the probability distribution. This is simple mathematical framework. This mathematical framework is called the quantum mechanical framework, and this till today fantastically explain each and every aspect of the modern experiment. Till today, there is not even a single discrepancy of this formalism, and whatever we are enjoying, this laptops or whatever I'm talking, and then light, every technological development is because of the quantum mechanical understanding of the microscopic world. It fantastically explains the microscopic world. This is the framework. Okay, my plan now is one way I am giving the bigger picture, and in the some way I wanted to concentrate what type of questions within the quantum mechanics addresses, and how it moved in the historically, and what was the outcome of this change in our view of the world provided. So for that, from now onwards, I will little bit go into the details. I'll pick a few papers and then try to explain it. If you're not able to understand, you can ask the questions later at any time. I'm going to pick this famous paper it's called EPR paradox. E by Einstein, Podolsky, and Rosen. So this is famously called EPR paradox. And the fantastic paper, in quantum mechanical description of physical reality, be considered complete. It's published in 1935. Let me go through with this. So there are the many interesting words like physical reality can be complete, and description. So there are many interesting words. Let's try to understand. And these are all exactly copied from the paper. So these are all the EPR's sentences, not mine. I already explained what is a theory. So there is a observed world, and you have a mathematical theory describing that observed world. They ask this question. In attempting to judge the success of a physical theory, we may ask ourselves two questions. Is the theory correct? The second thing is the description given by the theory complete? I've explained already. That means there is an observed world and there is a theory. Theory is a mathematical construct. When is the theory is correct? If it can always, or someone will go to an experiment and he does an experiment, and then you have the prediction or data table. If the mathematical framework which you are explaining is exactly fits with this one, fits with the 1 minute, sorry. Am I audible?
Yes.
Yes, sir.
Yeah. Sorry, because whether I am in online or not, I just wanted to check that. That's why. Thank you. Okay. So, is the theory correct? What does it mean by is the theory correct? So, someone goes to an experiment and he does an experiment, he gets the statistics, and then there is a mathematical theory. You cross verify whether the statistics is exactly matches with the experiment. If that doesn't matches, then your theory is useless. It is incorrect. So, theory is correct. Quantum mechanics perfectly explains all the experiments till today. So, it is correct. Next question. Is the description given by the theory complete? Here is the trick. What do you mean by complete? Okay. The completeness seems to be there is a one requirement of necessary one to say that this theory is complete. What is that necessary one? Provided by EPR, Einstein Podolsky. Every element of physical reality must have a counterpart in the physical theory. Perfect. So then again the question, what does it mean? If there is some physical reality, that physical reality must be exist in your physical theory. That means in your physical model. Okay. Then there is a question. What is physical reality? How do I do that? Okay. Then comes the proposition of physical reality. They define it like this. If without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. I'll give you an example. So there is a chair in room. Nobody has disturbed that chair, and when you opened the room, chair was there. That means that nobody has disturbed because room is being locked, so chair was there. So an element of reality can be ascribed to that chair or the chair's position or the chair's color, whatever it may be. That means if without any way disturbing a system, if you are able to access that property, then that property is an element of physical reality. That element of physical reality exists. That is the characterization what they made. So that's what they call it as a that's physical reality. That is the element of physical reality that should be ascribed. That means if this such a physical reality exists, then in a mathematical theory it should be reflected. That's the requirement Einstein Podolsky are submitting. And then they show that with a very simple experiment, quantum mechanics is incomplete. Let me go with there is a mathematical expression, entangled state, and all other things, and I am now making it in a different experiment. Imagine there is a one person who is sitting in Bangalore, and he is creating two electrons. Okay, so one of the electron is carried by Alavelu in the Tirupati, and another electron is being carried by Babu, so he can go to outside the galaxy or Gauri Vidnuru or wherever he wants to. So he can be in a very spatially separated distance. And their clocks are synced, so they can do simultaneously an experiment. So the experiments, they are imagined like this. So every 15 minutes, like every 5 minutes. So every 5 minutes, I do an experiment. So the experiment is like this. So let's imagine in order to communicate in a simple language, instead of spin and other things, I am using a property called color and shape. Okay, so electrons doesn't have this color and shape, but in order to convey, I am using this notation instead of spin and other things. Okay, so now imagine that electron has a color called green and red, and it also has the shape circle and triangle. Okay, that means it has a two properties. One is color and another one is shape. Understand that. So two electrons, one of the electron is carried out by Alavelu in one place, and another electron is carried out by Babu in another place. They both are spatially separated, and each one is having two properties. One is color and shape. Color can take two values. That means it can be green or it can be red. Shapes can be two, either circle or triangle. These two electrons are such that whenever Alavelu measures the color, and if within the Alavelu slab, if Alavelu gets green, then definitely if Babu makes the measurement and if Babu measures the color, then he always gets the red. When that means opposite, always they get the opposite. Okay, you understanding? So whenever Alavelu gets the green, Babu always gets the red. Whenever Alavelu gets the red, Babu always gets the green whenever she measures. Similarly, the shapes are also correlated. Whenever Alavelu gets a 0, then it's circle, Babu gets the triangle, and if it is getting the triangle, Babu gets the circle. That means Alavelu, imagine they are in a faraway distance. This state and this feature is called entanglement. This is called entanglement. Whatever Alavelu does instantaneously will be affected in some way, influenced by the Babu. So whenever Alavelu gets the green, its Babu gets the red. Whenever Alavelu gets the red, Babu gets the green. Like that, any property, not just two properties, the infinite properties are all correlated. This is called the entanglement, and this entanglement is the property which is making quantum mechanics, quantum computation, quantum information, whatever exists. This is very, very necessary. Without entanglement, you cannot. There won't be any information theory. There won't be any computation. Okay, so this is the name given by Schrodinger, entanglement. Okay, so what I mean to say is that Alavelu, without disturbing Babu's, she doesn't do anything about the Babu system, but she can always know what Babu will get without even measuring the Babus. Because if she gets green, then she'll know Babus will be red, and similarly, if it is red, it will be ground. That means without disturbing, you can assign these properties. That means even before observation, electrons possess these properties. This is the conclusion. That means there exist realistic values before even the measurement. But quantum mechanics says that these two properties cannot be jointly knowable. Einstein concluded that because there exists something, an element of reality inherently, but the framework or the theory, quantum mechanics, imposes the restriction not to measure it jointly. That means your theory is incomplete. Quantum mechanics is incomplete because it is not able to provide the complete description of the physical reality of the world. That was his conclusion, and there were search for then people go on giving the more detailed explanation. So can we then comes with the question, what is called, if it is incomplete, can I make it complete? So how can I make it complete? This is the story. You can add some more information so that it can be made complete, and all those begin. But a great revolutionary idea come from John S. Bell in the 1964, and what we normally call him as the father of second quantum revolution, because whatever the technological applications, what we are seeing is basically from the quantum mechanics of 1930s, and what we are going to see is after 1960s. So this is what we call the second quantum revolution, and he come up with what today we call Bell's theorem. Okay, so what is this Bell's theorem? It gives a complete restriction that what, in some sense, you cannot complete the quantum mechanics. So there was some restrictions of completing the quantum mechanics. Quantum mechanical predictions are inherently in conflict with some of our classical intuition. What he suggested, what is the why this theorem is great is that Einstein was looking a classical world, that means how we look through our eyes, and then he was thinking that it should be fitted by the quantum mechanics. You are understanding? I hope you understand. That means ನಾವು ನೋಡ್ತಾ ಇರುವ ಪ್ರಪಂಚವನ್ನೇ ಪ್ರಪಂಚವನ್ನ ನೋಡಿಕೊಂಡು ಇದು ಹೇಗಿದೆಯೋ ಅದೇ ರೀತಿಯೇ ಕ್ವಾಂಟಮ್ ಮೆಕ್ಯಾನಿಕ್ಸ್ ನ ಮುಖಾಂತರ ನೋಡಿದ್ರೆ ಕೂಡ ಇರಬೇಕು ಅಂತ ಬಯಸಿ ಕ್ವಾಂಟಮ್ ಮೆಕ್ಯಾನಿಕ್ಸ್ ಇನ್ಕಂಪ್ಲೀಟ್ ಅಂತ ಹೇಳ್ತಾ ಇದ್ದಾರೆ. But that's not an essential way. So, but the essential view is that the microscopic world, the deeper physics, the microscopic world may not be the way how we see our classical world. It may be entirely different. That view comes from the Bell, and that's famously called the Bell's theorem. So what is the Bell's theorem? Before Bell's theorem, we need to divide. Let me give this division. Is the theory is being divided into operational theory and ontological theory. Little technical word I have to use it. Sorry, excuse. Operational theory means what we know, what we observe. That means all our classical world, or whatever the experiment we are going to do, an experimental lab, we do something and we get that. So in fact, quantum mechanics is also an operational theory because we know everything about the quantum mechanics. Then ontological theory. Ontological theory is that we don't know. We presuppose that. So it may be like what is ontology of this world? That means what is this world is made up of? What this universe is made up of? Is it an electron? If it is electron, what is it electron is all about? Like that. That's what the ontological theory. Bell come up with three assumptions, and he proves that these three assumptions in conjugation are incompatible with the predictions of quantum mechanics. I'll try to explain what these three assumptions. These three assumptions are: one is determinism or realism. What is the realism? Whether I observe or not, if I observe something, then that element of my observation exists before my observation also. ಅಂದ್ರೆ ನಾನೀಗ ಒಂದು ಲೋಟನೋ ಅಥವಾ ಕಲರು ನನ್ನ ಮನೇನೋ ಅಥವಾ ನೀವು ನಾನು ಮಾತು ಕೇಳ್ತಾ ಇದ್ದೀರಾ ಅಂತಂದ್ರೆ ನಾನು ಇಲ್ಲಿ ಇದ್ದೀನಿ ಅಂತ ಅಂದ್ರೆ ನಾವು ನೋಡದೇ ಇರುವ ನಾನು ನೋಡಿದ್ದೀನಿ ಅಂತಂದ್ರೆ ಏನೋ ಒಂದು ನೋಡಿದ್ದೀನಿ, ನೋಡುವುದಕ್ಕೂ ಮುಂಚೆ ಇದೆ ಅಂತ ನಾನು ನೋಡುವುದರಿಂದ ಅದು ಬಂದಿಲ್ಲ ಅಂತ. So because of my observation, the value is not created. So I am just observing something already exists. So that's the assumption of realism. And the second one is the local causality. What does it mean by local causality? Nothing can instantaneously influence something else. Andre, that means if something is happening at one spatio-temporal position, it cannot instantaneously influence someone in the very distant person. Something in the Tirupati cannot influence instantly the people in the Gauri. It takes some time. Okay, so that is what is called the local causality, and it comes from the special theory of relativity and other things. And there is something, the way some assumption called free will or measurement independence. Everyone has a free will. Let's not go into detail, but these two are the very important assumptions. And Bell proves that the local realistic models are incompatible with the predictions of quantum mechanics. That means the predictions of quantum mechanics are not compatible with these two assumptions in together. You taken together, conjugation. That means 1 and 2 and 3 implies some C, and the negation of C is what is the prediction by quantum mechanics. So either you have to reject 1 or 2 or 3, because this is very successfully experimentally many people have done many experiments from 1987. Always this is true. So if we go with the experimental result, one has to reject either the realism or local causality, or both together. But the minimal is one has to reject the realism. That means before my observation, the result was not there. Just because of my observation, the outcomes or the result emerge just because of my observation. I observe so that the world is. If I am not observing, no world is. So it's a very looks like very philosophical, but that's what actually the quantum mechanics is all about. Or instantaneously it is affecting others. So that instantaneously affecting is bit difficult to tackle. So it's better to leave out the realism or determinism. That means before my observation something was there is wrong. It's better to accept that my observation created the result. My observation created the world. So this feature is what is essential. So you might think that why I am speaking about this one. It looks like too philosophical and all of that. But let me tell you, this is the core importance of today's security. All defense industries, defense and everything are ready to spend thousands of crores for secure information transfer, and that secure information transfer is coming because of the Bell's theorem. And Bell was not at all interested in this question. Bell was very interested in what is all our world is made up of. What is quantum mechanics is trying to tell us about nature's nature. But what is it now? Why it is technologically important? All the quantum mechanical security, information theoretic security, cryptography, everything is because of the Bell's theorem. And in fact, it changed our world. Okay, let me move. Otherwise, I'll be content. So there are many interpretations of these results. So what I'm saying is very minimal explanation. So there are many different explanations. So one is called Bohmian series, collapse, relative state interpretation. There are many worlds interpretation, vaguely saying that so cubism, which says that in some sense everything is degree of our belief. So the state reality is our degree of belief. So it's interesting in its own sense. But this is the mathematical framework, and this is the foundational insight which is giving rise to the computational speed in the quantum computers and giving the security in quantum information, and which is going to drive the industry for another 30 years. Okay, so that's one small break. Yeah, that's the main important thing. And then historically, after 1965, what happened? Again, in 1985, the first paper on quantum computation came, which is by David Deutsch. And in fact, David Deutsch was primarily interested to understand which of these, there are many interpretations. So as I told you, and he was a proponent of many worlds interpretation. He wanted to see that out of this interpretation, many world interpretation was the one which is success, which is correct interpretation. That was his motivation, but he ended up with giving us a quantum computer. So this is the first paper in the quantum computation thing, and this is algorithm proposed by him is called the Deutsch algorithm, the famous Deutsch and Deutsch algorithm. Sorry. And next is the famous information theory, quantum information. So this is the time. This is the beginning of quantum computation, 1985, and quantum information theory. That means information transfer is started in 1993 by the publication of this famous paper, which is the teleportation of the quantum state between two, just by making one phone call. That means by making the classical communication, one can transfer the quantum information. I'm not going into detail because teleportation itself is very interesting. In some sense, the information transfer. So through the classical channel. That's That's what the teleportation is. And that gave the birth of quantum information theory. And a big blow come in the 1994 by Peter Shor, who proposed the algorithm of factoring and discrete logarithm, because all our classical cryptography is basically based on RSA and this factoring and logarithms. And he showed that that can be easily brokeable by the quantum computer. So one has to develop the different aspects of encoding and cryptography and all other things. So it's a 1994. Now we are in which era? So now we are in, it's a era called NISQ era. And of course it is when it was 2018. Yeah, still we are in that. It's called NISQ computers, noisy intermediate scale quantum computer. Current record is 128 qubits, 128 qubits by IBM. IBM is having 128, and it's going to increase, and it's a very short increase from the last 10 years. Definitely, it's going to be rule the world for another century, I suppose. There are many other, I just told one essence because I just wanted to concentrate and give the flavor of what type of questions we ask within the quantum information theory computation, and why it is important and all those things. So that's why I picked it up, and also it was historically important to understand. And there are many other important features of quantum mechanics like uncertainty, randomness. Here the randomness is, it's called a true randomness, in the sense that other randomness is because of the computational complexity of the function which you are using in the computer. But and that means anybody who is genius can crack that randomness. So your OTPs and everything can be cracked. But if the randomness coming out of quantum mechanics, quantum computer or quantum mechanics cannot be cracked by anyone. So it's a true randomness. And there are many already the random number generators are market available, and many banks and all other things have started to use. Entanglement, I have already explained it, what it is, and this is the one crux of all information exchange. And there is other thing called no cloning. There cannot be a Xerox machines, quantum Xerox machines kind of things. So information is very safe. And there are many, so these are the research level questions nowadays people are asking, and then still it is going on. So indefinite causal orders. So this is interesting in the sense that we always have the causal order. For example, I am speaking, I am first and you are next. I am speaking and then you are listening, or you are speaking and I am listening. So there are the features you call the temporal superposition. So both can be superposed. Temporal orders can be superposed. And we all heard about wave function, which is mathematical representation. Is it a real or epistemic? So, and there is a big problem which I have not even touched. It's called measurement problem. So that means, are we in a quantum superposition? So why are we not in a superposition? So is there Aravinda now sitting here and another Aravinda sitting in another galaxy? Are we in superposition? So why can't our superposition be observed? Is this classical world is also explained by quantum world? So why the collapse? And between, there are many other possible theories, but why nature is chosen quantum? Why not others? So what is it? What is the physical axioms, physical reasons for nature to choose the quantum mechanics explanations? So that's where the physical axioms. And one most important question, which not even we are in a position to properly we are informed. Question can be formulated and answer the question: why quantum computers are so powerful? Where is this power is coming from? What is the feature of quantum mechanics which is giving you such an enormous power? So that's all about our talk, and thank you for listening. And this is just in India, there are a few groups which are rigorously working on quantum information theory and computation in Bangalore, Raman Research Institute and RRI. These are the two places. some 3-4 faculties are working on this area, both experimentation and theoretical. I am more into theory, so I am a theoretician. So I do pen and paper, pencil calculations. So I know these people, and then IIT Madras has a very good group, IIT Bombay, and of course IIT Tirupati, and Institute of Mathematical Sciences Chennai is having a very good group, and ICER, Indian Institute of Science Education and Research Pune and Mohali has the best groups, and Indian Statistical Institute Kolkata, Satyendranath Bose Center for Basic Sciences Kolkata, and Harishchandra Research Institute Allahabad. These are the few places, so there are many other places also. So I'm just indicating a few places. So thank you for all.
Thank you, Arvind. Just unmute everyone. If any questions, you can unmute and ask the questions. Srinath sir, or
Yeah, thank you. It was really, of course, our brainstorming kind of a session, because we used to listen such kind of a talks within the four walls of a premier institute, which you have mentioned. Of course, in Bangalore, in our college days, we used to also hear from Usha and many other Shrikant and many other people from other institutes. Thank you for refreshing our the learning of a quantum mechanics, which we have done in our what you call regular education. It's a good work done by you, Arvind. Thank you, and I am very grateful because I am sitting in a village. I could able to listen what was the special privilege to be inside a college. I am in a village which is next to Arvind's village. Supriya is sitting in a Gauri Vidur. So this is what the technology is helping us. Hope in future quantum computation and high speed internet, which is going to come, will help us. This is my initial remarks on small.
sir, muted sir.
Physical thing in physical reality. There was a statement with respect to that, considering the Big Bang and the detection of gravitational waves. Considering these two aspects, whether this physical theory and reality unidirectional or a bidirectional, what kind of a relation a physics mind can think of? Just a commentary I would look forward, Arvind. Thank you.
Yeah,
Arvind.
thanks.
Arvind?
sir.
ಕೆಲಸ ಇದೆಯಪ್ಪ?
ಸರ್ ಕೇಳಿಸ್ತದೆ.
ತುಂಬಾ ಸಂತೋಷನಪ್ಪ ನೋಡಿದ್ದು.
Thank you.
2004 PUC?
sir. Yes, sir.
2004. ಸರ್ ತುಂಬಾ ಸಂತೋಷನಪ್ಪ ನೋಡಿದ್ದು. Very happy to listen your physics. Of course, I am very weak in physics.
Yes, sir, correct.
ಸಂತೋಷ ಆಗಿ ಗುರುಗಳು ನೋಡಿದ್ದಾಯ್ತು. MS ಅವರು ಇದ್ದಾರೆ, ಡಾಕ್ಟರ್ ಜಿ ಅವರು ಇದ್ದಾರೆ, ಶ್ರೀನಾಥ್ ಇದ್ದಾರೆ. ತುಂಬಾ ಸಂತೋಷ ಆಯ್ತು.
Thank you, sir.
Fine. ಸರಿ, ಬಂದಾಗ ಬಾಪ ಗೌರಿಬಿದ್ನವ್ರು.
Sure, sir. Thank you, sir.
My invitation to visit my college.
Sure, sir. Thank you, sir.
Principal at Government PU College, Deepala, where Srinatha is a SBC member.
Yes, sir.
He is helping a lot. And the same thing I expecting from your side also.
Yes, sir. Sure.
So please come, I will inform. So I will create a school and I will inform you. So please come out to our college.
Sure.
Okay. God bless you. God bless you.
Yes, Srinatana. Yes, I'll try to explain. But before that, I just want to thank MS sir is here. So I was expecting him. Starting al nodlilla. So thank you, sir. All my physics interest is because of his teaching in National College. I still remember the way the artistic beauty of deriving an equation used to be there in the full board, starting from that side to this side. The step by step, so clean derivation of some equations. I used to get creative beauty even in deriving the equation. That's what I enjoyed his classes. So thank you, sir. Thanks for teaching us such a great physics. I was so lucky to hear the physics from you. Okay, so thank you. Srinatana, that question is a bit tricky because there are a lot of questions concerning even within the cosmological model itself, because that model itself is not settled. The Big Bang is one model, and there are many alternative models are there. So unless that itself is being settled there, one cannot track those questions. The second thing is the biggest problem and biggest challenging the quantum gravity, quantizing the gravity. The people are thinking, what they are thinking now is a fundamental relook is needed. It's not just quantizing the gravity. So one has to take from what is our notion of space-time. Okay, so we think that time is unidirectional, and there are many those classical notions doesn't fit. Okay, for example, nowadays I was doing research in the sense that one can be just like a spatial entanglement. There is a possibility of entangling the temporal scenario. That means my present is not just a present. My present is entangled with my past and entangled with my future and entangled with everyone. So the entire space-time itself is considered as a quantum state. So within that aspect, it's a complicated and very interesting question.
Now, one supplement is like how many in Indian scenario, how many people are working in this particular specialized field? What is the prospectus for the future students? Just
okay.
Few.
Yeah, see, as you have all heard about, there was Indian government has planned to release some nearly 8,000 crores of money for quantum computational technology. Okay, so now human resource is considered, it's very, very, very less. Within India, as for the faculty is concerned, I would say some 20 to 30 people at most.
Yeah, that's the reason I asked. It's very full.
Yeah, even the number of institutes, you can see that, and in each institute, maybe what I mean to say is that some 2 people or 3 people. So if you consider totally, you'll hardly get some 20 to 30 faculties who are working in this area. But industry demand will be huge because already industries are started to recruit it. So this is the right time for both the students who are in the masters or in the PhD or even in the BTech and all. We ourselves are offering some of the online courses in the computation and other things, quantum computing. So one has to imagine this is 1982 in the classical computation. Okay. Even not only for this people, even for if someone is planning to think about any startups, okay, startups or industry or any other thing, this is the right time, because who knows who is going to be in Infosys next another 20 years. So that is the status we are in.
Thank you, Aravind. It's fantastic to listen to you. Hope you take others' question.
Yeah, thank you.
Girish can speak. Girish can speak. Girish has raised hand. Girish, please.
Aravind, thank you very much for the wonderful talk. And I actually echo your sentiments on Professor Muhammad Salim. So MS is our reason why I am in physics. So otherwise, I would have been in mathematics, or maybe I don't even know whether I would have been continued in research. Anyway, I am not I'm not as good as you for talking about cosmology, gravitational waves, and other things. I have a very naive question, very simple question. So when you talk about computation, normal computation, and classic quantum computation, so we talk about bits and qubits. So whatever the bits what we talk, they're basically information carriers only. Just by shifting from binary to quantum qubits, how did the speed of computation increases by so many? Like
But binary it is either 0 or 1. Okay, but in quantum it is 0 and 1. So it's infinite. Not binary is just 0 or 1, only 2. Whereas in quantum it's 0 and 1. That 0 and 1 can be anything. Whatever that infinite way you can keep 0 and 1.
Yeah, but that's basically only information carrier, right? But actual calculation still depends on some processor or something.
Yes.
Limitation factor again.
Yes, but that information, how much it can carry? For example, bit, how much information it can carry? So it can carry only 1 bit of information. I mean, if it is 0 or 1, it can carry 1 bit of information, classical information. But in order to carry the complete infinite amount of information in the classical system, it requires infinite amount of information storage capability. But the quantum can, 1 qubit, I don't say that 1 qubit can store the infinite classical information. That's also a wrong statement, because there is inherent limits even in the quantum computation also, that it cannot outperform. It cannot, what I mean to say is that there is classical computational complexity classes like P, NP, and all other things. Tomorrow it's not going to explode everything. But there are the two aspects which is giving rise to the superpower for quantum computation. One is superposition. More than that, second is entanglement. That entanglement is what is giving rise to, in some sense, what is giving rise to the superpower.
Okay. So basically, if we can put a limit on, say, qubit also, kind of information it carries, that's the number of times we can actually process it. So it's not that it can be.
Yeah, it cannot be infinitely powerful. Its power is also limited.
Okay. Perfect. Thank you. Thank you, Aravind.
I think you can take question from chat box. There are 2 questions. If you can see the chat box. Then we will ask Harsha to ask after the chat box. You want me to read out, or you can read it?
Yeah. Is there any theoretical expression which predicts the inhibition of quantum eavesdropping? Color is not a physical quantity. No. This color and all I've just used. Actually, I should have used sigma x and sigma z. That is what I mean to say is that it's a Pauli spin operator in up and down and other things. That confuses the general audience. I don't want to use more technical terms. So it is easy to understand color and shape. So that I used color and shape. Color and shape is just a property in order to indicate that this is the property. Whereas in quantum mechanical systems, there are infinitely different properties. I don't want to be more technical, so that's why I used the color. And
second question.
Can an atom hold information? Yes, all this is. There are systems called ion traps, where atoms in the form of ions is being trapped in a magnetic field, and that's where the quantum computation happens. And of course, I will not explain what is the physical model of a quantum computer, because that will take completely one more huge lectures, because there are many platforms. It's a superconductors, and then nitrogen vacancy sentence in diamond, NMR, ion traps. Each company is using their own computer, so that it's not yet hardware is still running on. Research is still going on.
Yeah, Dr. Sita can ask now.
Thank you, Mr. Dr. Aravinda, for the very lucid talk. At least the basics we could understand very well, even though, you tried to put it in terms of the physical things, and it was very nice.
Thank you.
But I just wanted to ask, is entanglement actually advantage, or actually we should dissociate the entanglement? I mean, because entanglement in some way is, if one person is transmitting to particular other person, then entanglement helps in understanding. But suppose you want to transmit something which can be accessed by somebody, but
what I mean to say
that is one thing. And then I also wanted to ask, one more thing is that just like we in physics, in the real world, we can understand most of the things by classical mechanics. We don't have to go to quantum mechanics. Will that be the same with even quantum computing and quantum communication, etc.? We will be transparent. We don't know how it goes, but so we don't have to understand all that. I mean, will that be the case, or will the whole thing change fully?
Yeah. Okay. The first question is that without entanglement, no secure information is possible. No quantum computation is possible. And the entanglement is the feature which doesn't exist in the classical world. That exists only in the quantum world. Only in the subatomic level only it exists. So that's giving the power for everything. This is the first thing. The second thing is that classical world is a subset. What I mean to say is that what have we explained? So one throwing a stone, that's all we can explain with the classical world or the buildings. Our computers we cannot explain. How I am communicating from here and how Srinath is sitting and then listening. That cannot be explained by classical mechanics. None of our transistors cannot be explained by classical mechanics. None of our technologies can be explained by classical mechanics. Classical mechanics can only explain if I throw a ball, it can go. Of course, classical mechanics as a theory, it is the most beautiful theory, I accept. But yeah, everything universe is actually quantum mechanical. Classical mechanical emerges just because of our noise in the observation. That's it. It's a subset. It is a small set. Quantum is the big one. Because of our inability, to be very frank, our inability to observe the quantum world is what is giving you a classical world.
Aravind,
Yeah,
Yes.
thank you very much for the very nice talk.
Professor GV can speak. He is a very senior most scientist and is a lecturer from National College. Sir, please, sir.
Thank you, sir. Thank you.
Aravind, it was a very nice talk. And I was unfortunate that I was born a little earlier so that I could not be a teacher to you.
Sorry, sir.
Mr. Salim was my colleague earlier. And I am glad to hear that you are inspired by Salim and others. Wonderful.
Sir. NR was there and
yes, wonderful. It was a nice talk. And of course, the quantum mechanics is not very easy to understand, I know, but you have made it very simple and giving the examples like color instead of the parameters. Physical parameters you have represented in terms of color, size, and things like that, which makes things very clearer for even ordinary common man. Of course, I can't say that everyone can understand this, but a person with some physics background can be he can able to understand see the talk. It was very nice. Congratulations.
Thank you, sir. Thank you.
May I ask Sir MS to make any comment before we go to the next?
Sir,
Is time
maybe
up?
sir is not in the list. No, sir.
Fine. No problem. No problem. Akash, are you there? You want to make any observation, Akash?
Yeah. Oh, Akash is also one of my closest and very good friend. We used to spend a lot of time in
Akash,
IIS.
are you in a... Akash, are you in a...
Thank you, Arvind, for your wonderful talk. I don't have any questions. I just want to say congratulations. Thanks, Arvind.
Thank you. Anyone wish to ask a question, you are free to do. Otherwise, Supriya, over to you. If time permits, you can continue or you can wrap the session.
Any questions? Okay. We will end here. And I call Rashi Priya, who is a creative volunteer. She will present vote of thanks. Over to Rashi.
Madam, just want to interrupt.
Yes, Akash, please do.
I request Aravinda to write about these things in Kannada for Kannada readers.
That's a good idea. I think
because in one talk, it is very difficult for everyone to grasp the fundamentals. But if he writes it as a series or as a small book, that would be quite helpful.
Also where he writes a lot of things.
Yeah, that is anyway. He has his own blog. He can share that information in his blog also.
It's a good idea. Maybe Aravind can consider.
Yeah, thanks, Akash. I will do that. It's yeah, thanks.
Thank you.
The Thanksgiving thing.
Rashi?
Yes, ma'am. Good evening, everyone. I'm Rashi Priya R. It gives me an immense pleasure to deliver vote of thanks. I'm glad to render thanks to our distinguished speaker, Dr. Aravinda S, Theoretical Physicist, Assistant Professor, Department of Physics, Indian Institute of Technology, Tirupati, who has captured our concentration towards the concept and filled us with knowledge of quantums and its magic. Thank you, sir. I would like to thank our creative resource persons who are present here, and I am grateful to our creative associates, volunteers, and participants. Thank you, everyone, for giving this opportunity. Over to Supriya.
Thank you, Rashi. Thank you, Rashi. Thank you, Arvind. Thank you very much. Okay.
Thank you all for this thing. Yeah.
Okay.
Recording
ending
because
the
stop ಮಾಡಬಹುದು. No.
Yes, I will send you.
No. ಒಂದು ನಿಮಿಷ.
Okay.